Oh my god, I have
no idea. Ja, schau mal, das ist tatsächlich
today's the only day we have about an hour.
really
Come on. It's very cramped. It's very weird. I am
Nein,
also in the old building.
also das wäre das straight I don't know. We get an hour in music, right? I have an hour in music. Was? You have two brain. Meine hier. What? We still throw. Ich kann Deutsche machen. Can I get the gift from you?
That was my last one.
That was terminar.
I was actually sad. I was like, I want to something sketchy.
Paso, pero ajá, ya la nota. Ya fue.
I think all three of them are. I'm not sad. Yeah, that's what you want.
He might be something in there went my spiel.
Something like 4 hours.
These are recipes. But I feel like he's really hard. I feel like
Conversation.
But I don't think they have those. Like they had the chat.
It looks horrible. You
I'm so happy. I mean, I'm serious.
Very actually.
My name is Frank Venmans. I'll be your teacher in the coming 5 weeks. So I'm thinking on how to organize this. So there is this new trend of making two projections in one classroom. So sometimes I'm going to show. So I was considering if everybody could move here, but I think it's not going to be enough place. 3, 7, 10, 13. Let's keep it simple. So I'll disadvantage everybody by doing a bit both sides. Yeah, the best seats are therefore in the middle. So now you could. So those who are really at the extremities, please come and sit at the middle. These are the best seats. This week, these 5 weeks, we're gonna do dynamic methods, meaning that how to solve optima over time. And so today is, let me say, today is just theory. I'm gonna see 2 or 3 examples. Then next week it's optimal management of non-renewables, mainly oil. Then we'll do optimal management of renewables, mainly fish, but mathematically that's the same as forest or whatever renewable there is. Then we apply that to an economic model to find a framework for discounting. And week 5 is the social cost of carbon, and so the climate integrated assessment models. So that's actually my area. I do mainly integrated assessment models, apart from other things around carbon markets and offsets. So, okay, why study dynamic models? Welcome. No problem. I'm also apologizing for having shifted the timetable for today. That was because I need to go to a conference. So if you think about it, most important decisions actually have a time dimension. We rarely really develop that in economics because it's so horrible. So often we do like static supply, demand, logic. But many things depend over time. So savings, pension, human capital. So you're investing, you're poor today to be better off in the future. You could also, maybe you're studying too hard, you should enjoy more. Or maybe you're not studying hard enough. Like you're wasting your future. What is your optimum effort? Like, should you do 40-hour week or 45? We have a model. So this is like a standard economic question. Then there are firms who have capital stocks, managing their stocks. In our case, it's going to be stocks are oil, minerals, groundwater, stock pollutants like CO2. They all have this logic of a accumulation over time of goods or bad, and applies the same for renewables. So fish is going to be our main example. Groundwater, if there is inflow from rain, and renewable wildlife. There is an example of elephant management, forests, so optimal harvest in forests, etc. And so we need two types of solutions. So we want normative, like what is the optimal decrease of emissions to maximize welfare. It's not zero emissions tomorrow, but it's also not business as usual. Like what is best, but also positive answers, like how do people react, how do people save, and so once we know the dynamics of people's saving reaction function, we can put that in the model and see what it gives. Yeah. Or for example, how does a monopolist manage prices? That goes into the model, and we can predict how a monopolistic market will lead to a long-term equilibrium. A bit of explanation about the readings. Maybe it's important for everybody. I get many questions of the type like, do we need to read this or do we need to read that? So when you understand my slides, you're in a good place. So then that is 80% of what I aim for. Yeah. So then you can also read to understand my slides better, or to see examples and get more acquainted to the material. Yeah. But my exam is very much based on my slides, and then if I treat a paper on the slides, the paper will be in the readings, or etc. There will be. So in this case, we have introduction to optimal control. It's mainly the slides with more text. Then mathematics 4 to 6. If you have forgotten how to integrate functions, there are like a few examples of derivatives and functions. Then if you want to read in a chapter what we're going to see today, you have these 3 options. They're similarly good. One of the 3 is fine. And then if you want to go deeper, if this maybe is something to do with your dissertation or you want to. So there is this shiny book, which is very technical and very technical, but at the same time intuitive. So that is quite a quality for mathematics books. Very good. And then there are two other books you can have if you want to go deeper. Not needed for succeeding my question. Good. Mathematical recap. So let's refresh a few of the concepts that you've already seen in secondary school and in your preceding years. No? So notation, I will sometimes, so everything depends on time, except the parameters. So sometimes I write it this way, sometimes it's a subscript, and it's sometimes when it's obvious that it's a time-dependent variable, the subscript is left out. Now sometimes the condition at the terminal stage, at the last period, I will call that capital T. Then there will often be a time derivative. The change of a variable over time. Think of y being production. So how does production change over time? It's a derivative, and yeah, that's the definition of a time derivative. Yeah, it's the increment over time. Maybe a quick reminder. So we're working in continuous time. So the increment over time is small, but that does not mean that this speed becomes super small. So this is a speed, so the change of GDP, but another example would be the change of where you are. So it's the speed in kilometers per hour. So it's not because you're looking at an instantaneous speed, I'm now going at 60 kilometers per hour, that necessarily you're driving during an hour and then have delivered 60 kilometers. Yeah. So this is 60 kilometers per hour at a given point in time, or GDP growth per year, but applied to a given month. Yeah. You may have 2% over the year, but a faster growth and a slower growth, and so this 2% is initially 4%, then 1%, etc. Yeah. Good. Then we have the growth rate. If we have y dot over y, that is also technically the change of the log over time, and that's going to be your growth rate. Actually, my example of just before of the 3%, there was rather a growth rate than a pure change. The pure change would be dollars per year. I've increased the GDP by 50 million, so then the change over time is 50 million per year. And here we convert it into a percent growth rate. Chain rule for the derivative. So if I have a function, imagine production is a given function f of another function j of time, so then the chain rule tells me you take the derivative of the outer function times the derivative of the inner function. The derivative of the inner function is with respect to time, so that would be then the g dot. So let's take an example. We're going to use y. Imagine you have exponential growth at rate t. What is y dot? What is the change of y over time? So we have a function that's an exponential, and inside this function, the argument is just a linear function, r times t. So it will take the derivative with respect to the outer function, that's e to the power of t, times the derivative of the inner function times r. Yeah? And so that's it. Now, what if we have y is the log of x, and x depends on time. So the change, I have an hour function, the log, so that's 1 over x, and then times the derivative of the inner function, we get x. Okay? And yes.
I think it's 1 over x, not 1 over ln x.
Exactly. Sorry. And so yeah, that's just very correct. Let's see. No, yeah, that's it. Now, total versus partial derivatives. So consider a function y is a function of x and z. Maybe production is a function of capital and labor. Yeah. Then if you have a change in production, there can only be two drivers of that change. If in a simple world where production is just labor and capital, a function of those two arguments, any change in production must come from these arguments. So the small change in production is due to a change in one argument or the other, and you multiply by their respective gradients, the partial derivatives, to explain any change. Okay? Now, example, if y is just x times z, production is just labor times capital, any change in production is then, there must be, it's a sum of changes in both drivers or in both arguments. And so I have the partial derivative of this function with respect to x, z is remaining, and so I have this relatively simple solution of differentiation, of my production function. Yeah? So differentiation is actually the same as derivatives, but it's a concept that helps you understand derivatives with many arguments. Partial. Now, total versus partial derivatives of time. So this is a special case. Imagine now we have a argument x, and we also have time as an argument in itself. Maybe the only thing that matters for production is capital. But then there is also a time trend in TFP. Okay? So now we have an argument t, and we have then also capital, which depends on time, it changes over time. Okay? So now if we do the same logic, any change in production is due to a change in capital or the mere advancement of time. I'm going to assume that TFP just, like a man from heaven, like productivity grows by waiting. Yeah? So then we have the partial derivative with respect to capital, the partial derivative with respect to time, and we have the same expression. Okay? So, and I can divide everything by small increment of time so that the same expression is now expressed as a derivative. So the change over time of production is the partial derivative with respect to capital times the change of capital over time plus the partial derivative with respect to time as an explicit argument. Okay? This is called the partial derivative with respect to time. This is the total derivative with respect to time. So the total derivative of a thing, like maybe it's, let's keep it at production, is the effect of time on the underlying drivers, capital, plus maybe also a direct effect of time. The mere advancement of time may also change the function. Let's apply this. So we have so y depends on capital, but capital depends on is time dependent. We can build up capital and a function of time. Let's say so it is proportional. Our production is proportional to capital, but then there is also a growth rate called TFP, total productive. By just having time, production increases for a given level of capital. And so you will have the equation of motion tells you that capital just goes up linearly. It's a bit of weird, uncommon assumption, but I want to keep the function simple. Yeah? And so now, what is the partial derivative with respect to time? You can think of it. This is the, and you see until here. You can still move to the center if that would be better. The partial derivative with respect to time, I have time as an argument here, so the change of production with respect to just time is going to be t. Now I have, so first it's a product, then I have an exponential function, the derivative is the same exponential function, and then I multiply times the growth rate. I've done this already. Yeah. Now we also have, now for the total derivative, we have two terms. Okay. So I first have the derivative with respect to capital. So the total derivative is the one that I will write with a dot. Yeah. And so the derivative with respect to k, the partial derivative, is just e to the power gt times the time derivative of the argument of capital. So I've written this one. Now dk dt is alpha. And then I have the partial derivative. So these are the two drivers of my of production over time. And you can then rewrite it. So can you see this? Yeah, you can see it. So you can then substitute out production to give it a more interpretable form. Yeah. So to summarize, if I have a function of many arguments, to differentiate this function, I will say that any change of my left-hand side is due to the changes of both arguments on the right-hand side, and that the scale or the weight of these changes are the partial derivatives. Yeah. Good. Now, integrals. So I'm going to give you the simplest integral. Integrals are never simple. So, but still, to get the intuition, I want to give you an example of an integral so that to build up intuition. Yeah? So imagine we have a flow of water F over time. So we think of water as a stock, and it's also a flow. So F of time is maybe 1 square meter per second. That is a flow. Yeah? And it depends on time in the sense that maybe now it's 1 meter, but then at some point it's more or less. This flow changes over time. And I'm going to consider a sink. And by knowing how much comes in each second, I can also know how much there is in the sink, provided that I know how much there is in the sink at the start. So, by definition, if the flow is the change of the sink over time, if I have a flow of 1 square meter, cubic meter per second, then I know that after a second, there is a cubic meter extra in my sink, in my pond, or whatever sink I'm considering. So here is then some more information. Imagine there is 2 cubic meter in the sink times 0. This could be maybe a small pond. Then we have a flow of wastewater is added to the sink for 3 days. The flow starts at 0 cubic meter per day. I'm now expressing this per day, not per second. And increases linearly over time. And so here you see the flow over time. So on the x-axis we have time up to day 3, and flow initially there is nothing coming in. And then it's more and more and more and more over time until I have a large flow of 3 cubic meters per day. That is only on the last hour of the 3rd day. So the first hour of the 3rd day, I'm here, I'm at 2. And this continuously, it's like the example of my speed per hour. If I say 60 kilometers per hour, it doesn't necessarily mean that I'm driving an hour at a constant speed. It's a momentaneous speed, or a momentaneous flow, but that needs some unit of time to express it as a Good. So just as a hint, f is actually just t. I've made this function quite simple. Flow is just t. Starting at time 0, flow is 0. At time 3, flow is 3. So if I take the flow and I multiply it with an increment of time, I have how much water that comes in over that time. If that's an hour, then the flow times 1/24th of a day gives me the quantity that comes in that hour. And so another example, on average, the flow is half a cubic meter per. So if I look at day 1, ends at 1, but on average, I'm at half a cubic meter per day. So I can say day 1, I get half a cubic meter in my sink. Yeah, and so then I can also say what happens on day 2, what happens on day 3. So instead of looking at 3 days, I've considered 3 sub-periods, with each time an average flow. And I can calculate that, so that gives me more or less an approximation of how much I'm going to get at the end of day 3 in my pond. So the stock at day 3, terminal time, is the initial stock plus these individual contributions day by day. And so I started 2 cubic meter. I already explained first day it's going to be half a cubic meter per day on average. Second day 1.5, third day 2.5, etc. So I will have 6.5 cubic meter at the end of the day. Okay. So what is an integral? An integral is just this sum for a small interval. So I'm just gonna let delta t go to 0. Instead of looking at days, I'm now gonna look at hours and then at minutes and maybe seconds. And then what was initially an approximation becomes an exact solution. So I have the integral from time 0 to time 3 of a flow. This flow was actually just the temperature. So I get the integral of temperature. That is, the integral of T is T squared divided by 2. And so then the bounds are from 0 to 3. I can calculate it, and I have exactly 6.5. It's exactly the same because things are linear, and I took the exact mean of each period. So that was the trick. If this function is not linear, I will need an integral to get to better levels of precision. Yeah, but that is what an integral does. And so very often we're going to have an equation of motion for, I'm going to say the flow has this function, and now you need to integrate the flow to know the stock at the end. Very often the stock at the end is 0. It's a non-renewable, and so now you can know, it's going to be helpful. You're going to do this all the time. Okay, so this is the intuition behind what it means to have an integral. Good. I'm going to go fast over this. So I'm going to use this because my mouse here, because when I showed the boards, you're actually only half of the class will not see it. So let me go back. So the stock goes up quadratically because my flow is linear. So that is what you can see here. The stock starts at some S0, and this goes up linearly. And if I have, you probably remember that the derivative of a stock is the slope. So here I have a steep slope that is my 3. Here at the start I have slope 0, that is my 0. But then you can also, once I give you the flow, you can know the integral. The integral is the area under the curve. So this yellow part that has been added is the sum of all these small increments, and if I add them all up, I have the area, the yellow area under the curve. So if you think of, you know the flow, the area under the curve is going to give you the change in the stock by design. It's always the case. So the integral is the area under the curve, the derivative is the slope of the integral. Good. Questions? Yes.
Does that still mean that in order to find the total stock, we still need to find the stock at T0?
Yes. So I'm going to frame it a bit differently. If I don't tell you what is the initial stock, and I tell you at each second the flow, you can't know how much there is at the end. That is why just giving you a differential equation without an integrating constant, like fixing one point, you have no solution. I mean, you have a set of solutions. There are many solutions. So in this case, you are enabled to draw this line of the stock over time if I don't give you one point, fix you one point somewhere. So in this case, I said at 0 is here. I can as well say, I know that at the end of the day, it's going to be 6.5. You'll get the same solution. Or I can say at day 1, at the end of day 1, we're here. And again, you have pinpointed that allows you to find the solution. So that the integrating constant allows this to move this up. With the differential equation, I only give you the slope each point in time, and that doesn't fix the general height of the function. Yeah.
So just to understand that I got that correctly, it's just the intercept that this term gives us, like the shape of the slope we know by the
Differential
integral,
equation.
exactly, but the intercept we don't.
Exactly. So I've told you the differential equation. The change of the stock is t. I've given you this line, and then so you from there you can calculate this yellow distance. But then we need an integrating constant. We need to fix one point in time where we know the stock, so that we can say where it starts or where it ends or where it is at some point in time. Good. This was meant to be an intuitive example, and so let's formalize that a bit more. So I told you, so by definition, the flow is the change of the stock over time. So then, the easiest way that we're going to use is separation of variables to solve integrals. This is not a mathematics course on solving integrals, so I only use the ones that are easy to solve. So from here, technical trick, I bring dt to the other side. So now the left-hand side has only time, the right-hand side has only the stock, and I can integrate both sides. So if I know for every second in time this relationship also holds for many seconds in time that are accumulated, and so that is actually what I do by integrating. And then, as we discussed just before, we need an integrating constant to fix the level of this function. And so that's it. And we're going to apply that to a few functions, 2 or 3. But this is, we'll come back to this also. Good. Any questions? Then, the optimal control theorem. So this is the problem we will try to solve. So you maximize an integral. The integral is very often, in our case, always, it's utility. And that will be discounted. So this is the same as e to the power minus gt is very similar to 1 over 1 minus g to the power 1 plus g to the power t. Okay, so in discrete time we use this one. In continuous time we use this formula. They are for 1% growth. These things are really the same. Let me show you that this is actually a power function of t. This is actually also a power function of t. So the functional form is really the same. It's just that the j needs to be slightly adjusted to make them identical. Okay, so we're gonna always use this type of discount rate because it has an easy derivative and an integral. And so we added all utility over time. That's our welfare. Yeah? Macro models start this way also. We'll see macro models just. Now we know that, so utility depends on different things. Consumption in this case, like a flow variable. Capital, a stock variable. And then it can also depend on time in itself. We need the dynamics of the stock. So capital in the model that we will start with an economic savings model. So depend on how much you consume, how much capital you have already, and can have also time dependence in itself. As I said, maybe TFP growth. We need an initial condition or a terminal condition to get our integrated constant. And in this case, to make this a meaningful example, it's also the case that capital cannot be negative. But negativity constraints, we're not going to treat that, non-negativity constraints. One way to go with non-negativity constraints is you calculate the optimal solution without a constraint, and if it never goes negative, you're fine. Yeah? It's only, you need to manage constraints only when they're binding. In our examples, the capital will never go negative, so we have found a solution while respecting the constraint. Yeah? This welfare here, it's called the value function. Yeah?
It's a bit confused with the relationship and that you drew. Why is it the power of g minus 1, not 1 over g, and it is 1 over plus 1g?
It's a first order Taylor approximation. I can do that in the break. So actually, we're going to see this in week 4. So this is a first order Taylor approximation of that.
It's an exponential e that makes our relationship.
Sorry?
Is it because it's an exponential?
Yes.
Ah, okay. No.
Yeah, so this is my way of writing. So e to the power minus g is x. It is, yeah, a way of writing the exponential. Okay? Good. Now, the key slide. You should memorize this and, or more importantly, understand this. So there are going to be 3 equations to solve this problem. Yeah? Sorry. We first need an auxiliary concept that is called the Hamiltonian. And so it is defined as utility, instantaneous utility. So welfare is the sum of all utility over time, discounted. Now here we take immediate utility, instantaneous utility, plus forward-looking effects. So the Hamiltonian expresses the contribution of one period, or one small period, to the value function. So if my value function welfare is my sum of all my happiness. In a simple word, the only thing that makes me happy is eating. So the contribution of this day to my welfare is how much I eat today. That is my margin, my utility from whatever I consume. I might also have maybe some utility from capital that I own, maybe it's my house or so. And then I have future-looking effects. I might be saving. So then my savings go up, and that is contributes. That is how this day also contributes to my welfare. Yeah.
Is that like also another way to think about it? Would be like if the person's like perfectly rational agent, as like they're maximizing like future and present, so they're rational in terms of like, whereas really there's a discount on future.
Yes. So the simple so this is a model that allows a rational agent to maximize its welfare, given income and many things. Yeah.
It's basically a continuous Lagrangian.
Yes. So in discrete time, this would be the Lagrangian with all the different equations. Yes.
It's basically we are solving differential equation systems.
Yes. So what in discrete time would be difference equations becomes differential equations here. that should always give you the same, approximate the same solution. Nothing can change by changing from, nothing should change by changing from continuous time to discrete time. It's only that there are more integral solutions than discrete difference equation solutions. So this is a bit more simple in some regards, and then it's more complicated in other regards. But you should think of these as very similar. Once I bring this to a computer, I switch to discrete time with the Lagrange. Good. So the Hamiltonian is the contribution of one period to welfare, having two components, my immediate satisfaction plus the effect of this period to the future. And so maybe I increase my stock, and the stock is a good, so this is capital. I save, capital goes up, so this is positive, and mu is going to be a shadow price. It's the you should think of it as a Lagrangian multiplier. It is a shadow price, and it's how we value this increment over time. Yeah. Good. And so it expresses the trade-off that in many problems comes up between immediate satisfaction and future considerations. I can also unsave, like decrease my capital, so then this will be a negative term. And it's only optimal if I really enjoy my meal, my unsaving, or whatever I'm buying with my unsaving. So the mu, this Lagrangian, is called the co-state variable. State variable is scaling. Decision variable is consumption. And we'll see later that it's as I told already, it's how we value capital. So if I start my whole problem today and I say I have savings of 1,000, or I optimize my life with 1,001 as the starting capital, that's the marginal, that difference is by definition the value of mu. It's the marginal contribution of extra capital that I to my welfare, given that from there onwards I'm optimizing. We'll come back to this. So now we have the three equations that will allow you to solve this problem. So just to remember you, we defined the Hamiltonian as an auxiliary concept as utility plus then a shadow price times the growth dynamic. Yeah. Good. So at each point in time, I must choose consumption, my decision. I'm free to choose consumption however I like. Yeah, I can consume a lot, I can consume zero, but it should be such that I maximize my Hamiltonian. I can overconsume, meaning I'm depleting capital and I'm valuing it at below its shadow price, and so, or I can underconsume, my utility is too low, etc. Yeah? So whenever there is a way of consuming differently and your Hamiltonian, your contribution of this day to the whole welfare increases, you should do so. You should be at the optimum. So let me, I think I need this. So, if this is my Hamiltonian, and this is consumption, whenever I'm somewhere like here, and I can, by increasing consumption, improve my Hamiltonian, it's always, I always have to do that. Yeah? Or like if I'm beyond my optimum, is I consume less and my Hamiltonian increases, that is always better. Because it includes the forward-looking elements by the second term. Good. So we're gonna mostly use this one. We'll see in week 3 an example where actually might be flat. Like the maximization of the Hamiltonian is a bit more complicated. So this is the simple case, it's concave, and we have an interior optimum, but this is when it's not concave and you don't have an interior optimum, this still is a valid condition, but then it becomes the consumption for which the Hamiltonian is maximized. Good. So then we have a co-state equation showing us how things have to change over time, and here is the equation. So this equation is the one you should learn by heart, so to say. It tells you that the change of the shadow price minus the discount rate times the shadow price should be equal to minus the derivative of the Hamiltonian with respect to capital. And I'm going to reorganize this equation in a way that it makes that I can interpret what's going on. Yes.
The differentiation of the growth function, the discount price.
Not exactly. No. So this is the change of the shadow price. I'm going to find an equation that sets how the shadow price should change over time. So in a savings model, the shadow price is marginal utility. And so I'm going to have a solution that tells me how marginal utility should change over time. And from there, I find the optimal consumption path. We'll see examples later. But for now, I'm just going to explain the interpretation. Yeah? So my Hamiltonian has 2 terms. And so it will be the marginal utility with respect to capital, the stock variable, can also be oil or fish, stock. And it has the second term, like here is the Hamiltonian, so the growth also may depend on my stock. For fish, for example, if there's a lot of fish, it might grow faster than if I have almost no fish in the sea. For capital, if I have a lot of capital, maybe it could be the case that I get a bit of a monopolist or I get a private banker and my growth rate of capital might be larger if I have more capital. And then, so technically to go from here to the next, what I do is I divide by mu. Yeah? And so, what does it give? On an optimal path, let's draw an optimal. If I find an optimal solution for, imagine it's just capital. So savings model, optimal savings, and I will have this optimal solution. Since I have optimized, the fact that I would save a bit more here and bring it to the next period on an optimal path, that doesn't change my welfare. It's the same as I said for a static optimization. If you say, I'm here consuming, and this is just within one period, if I'm at the optimum, moving a bit to the left or to the right, I'm still at the optimum. I don't feel it. Whereas if I'm outside the optimum, moving left is bad, moving upward and to the right is good. I do feel it. I'm on a slope. Okay? This is the same logic in dynamic optimization. You have a path, and moving a small unit from year one to year next year, that shouldn't change on the optimal path. That is the portfolio balance condition. It's a no arbitrage condition. I cannot become better by redistributing over time my assets, my capital or my stock. Yeah. So imagine I postpone consumption. Yeah. So I do the opposite action. So I allow a small unit of capital extra here, and then I'll consume that next year. So what does it cost me? It's the opportunity cost of waiting. I get capital next year, and I'm impatient. So my discount rate is too impatient. I like it less. So that's the return on that I have to equate with other things that are changing. And there are three things that can change by postponing consumption, by having this capital later. One thing is maybe capital is useful. So maybe maybe I'm saving in the form of a jewel. And I like to show the jewel, and it makes me happy. So now I get, so utility depends on capital. It's less common. Think of a house. You would save, your asset would be a house, but actually you're also living in it. So then this is your avoid rent, yeah? The opportunity cost. Your direct utility depends on the stock. Now, maybe by having more capital, it grows at a different rate. So now the growth dynamics also depend on capital. In the standard model, the more capital you have, the more capital decays. So there's going to be the decay rate in there. The more capital you have, also the more return you get on your capital. So this is going to be the return. Like, the growth of capital depends on how much capital you have. That's this term. And then you have the fact that this is the shadow price of capital. So capital is going to come later. You're going to enjoy capital later, but the way you value capital can be different. So in a savings model, the shadow price is marginal utility. If I'm on a trajectory where there is growth, my marginal utility is lower and lower. Over time, I'm richer and much richer, and so my marginal utility is lower. So although I get the same return next year, I value it less because I'm rich. So that's the third term. So the shadow price of your stock may change over time. If I'm saving oil, that is can be interesting, but I have to take into account that I'm going to sell the oil at a different price next year than today. If the oil price is increasing, this is a positive term, and if it's decreasing, it's a negative. That's it. So this is, often I say this equation just learned by heart. It's the only one you have to learn by heart. But actually, it has a very intuitive interpretation. And you should understand this interpretation because when you solve a model and I ask you, like, explain what's going on, you have each time these three elements. Often there is only two or one, but it can, in principle, you can get one of the three elements that are the returns on postponing harvest or postponing consumption. Yeah. And then the third is a transversality condition. It's how to find the integrating constants. So we have to say something about the long run. If this is a model that is not sure. So we can do, so actually, so what we are maximizing is the value function, welfare. we can go to any fixed point in time, or very often for economics, it's infinity. So there is no end, like we're maximizing welfare until the indefinite future, but even then also we need to say how infinity looks like. That's the transversality condition, and that is the most basic one. Tells you make sure that the end is valueless. Your capital should be valueless. And for those who are from economics, this is actually the more precisely, if it's infinite time, the present value of capital should go to zero. Yeah? That means no Ponzi schemes. I cannot like borrow and then to pay my debt, borrow again and have this like exponentially increasing debt without like that. That is one way of thinking of a transversality condition. Yeah. Very often the stock, if it's like a fiscal stock, the stock cannot go below zero, so we have a bound on the stock, and this is going to be replaced by saying the stock cannot go below zero, or it's valueless, one of both. But if it has value and you have stopped your the end of your optimization period and you still valuable stock left, that can never be optimal. You should consume the stock. So then you get stock zero as a terminal condition. Good.
Sorry.
Yes.
A bit confused. So to satisfy the transversality condition, the future effect will be zero, is it? So the boundary will be the immediate gains in your Hamiltonian equation.
Can you please say it again?
In your Hamiltonian equation in the last slide,
Yeah.
the future effects will be zero in a steady state, and the immediate gains will be like a bounded kind of utility.
We have a whole 2 pages on transversality conditions. Let me say it. So the simplest case here is a case where we do not go to infinity. We go to a final, like there is an end of the world. Yeah. Imagine we know 2,100 atomic bomb and we're finished. By then, you don't want capital savings left. You should have consumed. If there is valuable stock left, no, it's the wrong. Stock is actually capital has a boundary. No, you cannot have negative capital. In the simplest model, your stock has no boundary. It's not really a physical stock. And then it tells you in a model where there is a finite time, you should make sure that this becomes, your stock variable becomes valueless. If not, you should have done less. Yeah. It's not that obvious to find an example. So if the stock is temperature, so cumulative emissions so then you can go to negative temperatures. There is no bound on temperature. And then you should make sure that the social cost of carbon becomes zero. Basically would then tell you zero warming. But a climate model that goes until a fixed time is actually not a very realistic model. We have no end of the world. So it's only the case when you know when the world ends that would apply. So we have many different cases. The more common one is that we hit the non-zero bound. That would be oil depletion. Now, another common one is for a capital model. We go to infinity. That's a model we're going to see in a bit. We get to a steady state. And so now this is actually the present value of the shadow price. It just tells me the shadow price cannot explode at a faster rate than the discount rate. If you apply that technically, you'll just find that you need to reach the steady state. The rest, all other paths would at some point have a shadow price that grows faster than the discount rate. So then it's replaced by go to the steady state. But I have like two slides in all the cases that will become clearer in once I do the particular case. So then we'll have a break because this is all a bit heavy, especially on week 1. So I'm very well aware of this. So let's take a 7 minutes break. And then, we'll start next Tuesday. Well past.
You realize that actually slides to
Yeah.
Had a good break? Yeah.
Also, I feel like foreseeable seminars, they were actually helping.
I think best on iPad. I think maybe taking it to iPad might be a little bit. I think I will pass, but you know, I think it was YouTube just explain like what the way makers were like. I genuinely
And the party series, which was fun. A little bit of an unexpected things on there.
very good. You everything good?
I love the new look though.
thank you so much.
You're the new. How are you? How was
The final was tougher than all the finals.
It was different.
We still
Very different.
You're like, okay, it's
Not very, but like I feel like the past 2 games but it was. We had the great so like
That's good. It's not just exam.
Yeah.
And it's not easy here.
Like you know, the resource income.
6 months.
Oh my god, what are going to have the exam? Oh my god.
No, we don't know when the exams are.
We never do until like 2 weeks.
Yeah, you have 20 points up.
Oh no.
Reunion already.
Just walking towards. No.
It's like every 5 years. But I'm not 5 years out.
I need to.
Okay. We had that was insane experience. It was like
You like stay.
no, like I think like but and it's like almost
It's super healthy.
it just meant like it was no because it was just like it was I think it's like just an insane experience. Like I know from primary school, but he wasn't in class, so he was not there, and he was okay. And I saw them. It's like
a bunch of like we talked to one of them and like I still don't understand what he does, but a lot of times like Dubai diamonds and like some form of, in my opinion, Ponzi scheme was going on with him and like digital marketing. Like, people from my primary school had a primary school reunion. Yeah.
And also they go out
So you moved today? You went to the Tower Bridge?
Anyone want any banana bread?
Chocolate milk all over my nose. I remember. Also pissed. Yeah.
Don't piss off.
I'm not
Just
Mann, er ist nicht auf das Halbparcours reingefahren.
situation, but it's not like
He's coming close. You can use like old things. Yes. I think
Wait for me. So this I'm right.
I'm gonna thank you. Next time.
Sleeping. Greek family. Getting back
actually was
I think it's right, it's about intuition. I think it's also one technique that you use the same I just need to get it. Whether it's staying this long.
I enjoyed it. Finally.
Yeah, but one. Mine is not here. I think it's the time change. I was when you said that I looked at next week is okay. Next week is the next but this week, for example, so whether there is next week, I think next week the same. Next week the seminar on right from today is the same. And next week they're gonna do
don't know how large you mean.
Love that.
How big?
We're going to start again. Please come in.
They are self-domesticated.
David, is someone in this?
Yeah.
Or that? And like if I don't see them, that's
Welcome for the second part. So there are seminars immediately after this lecture. If you have difficulty to be in your assigned seminar, you can switch because this is a special week. So there is one at 3, one at 4, and one at 5. Now this is a bit subject to space, no? Like because I don't know how big this room is. Good. So present value Hamiltonians. The key issue here is we don't care if it's a present value or a current value Hamiltonian. I have had like maybe 10 students coming to my office hours asking when do we need one Hamiltonian, when do we need the other? The answer is you don't care. You just use the method that is simplest and it gives you a different result. Somewhere there is a gap. So here is the present value Hamiltonian. So the only thing that is now happening is that we are not considering this a discount rate. So this, if there is no discount rate, this method also works. This is a method that comes from engineering or many science, many fields use optimal control. And so this is a more general case. So then it would also obviously, since this function is allowed to be a function of time, it applies also to discounted problems. Yeah? So f is now defined as utility discounted utility rather than utility itself. Good. So then I'm going to rewrite the same problem, and I'm going to be fast in the sense that sorry, now I'm having trouble. Yeah, it's here. So the only thing that changes is that you no longer have this minus delta lambda there. The minus delta lambda in the co-state equation that we're going to use is there because we have a discounted utility framework. So you can also have a non-discounted utility framework. Everything is the same, only this is now there is no discount rate adjustment. Okay? You can think of it as a problem with a zero discount rate, and you will get the same formula. So now we're going to show examples so that you becomes a bit more concrete what we're actually doing. So the first is the cake eating problem. It's a funny name for actually just oil exhaustion or non-renewables. Yeah. So we have a cake and we want to eat the cake optimally. But the cake is actually oil. Yeah? So simple model. We're going to see a better model next week. But bear with me. So this is So actually, I've called this is actually the simplest model in the world for optimal control. And I had a student on the evaluation, they said, we really don't like that you call this the simplest model in the world, because we have to acknowledge that it's very hard. So this is a hard model, but it's sadly the simplest dynamic setting you can imagine. Okay, so bear with me. We have stock S. Yeah, then we consume oil, C, we have a utility function, simple world, the only source of happiness is oil, and if we don't have oil, we are infinitely unhappy. Marginal utility at zero oil goes to minus infinity. Just to keep the boundaries simple, no? And we discount at rate delta. Good. So we maximize discounted utility from now until a fixed time t. And here is the stock dynamic. So whenever I consume a barrel of oil, I have one less. That's it. Yeah. So the time, if this is barrels per day, if I consume 10 barrels in a day, the next day I have my change in the stock is what I had minus the 10 barrels. Yeah. Good. And I know my stock initially.
Why is there now a fixed time period t here, not infinity?
So the logical thing to do is infinity. But the mathematically slightly more easy thing to do is to have a fixed time. But let's say also that infinity is also an allowed value. And we add an inequality constraint. So we're in this case where we say the stock variable cannot go below zero. So two things must happen in the long run. We exhaust the stock or it's valueless. But we're going to see it's not going to be valueless because we like oil in this so it needs to go to zero. That's the terminal condition. If you finish your optimization and there is some left, you could have done better. You could have consumed it. Yeah. Hotelling rule. So we have this Hamiltonian. So this is the general function, and so it's consumption, the utility from consuming oil minus the shadow price of oil, mu, and the quantity that we consume. So the change in the stock of oil is just what we've consumed. Good. And so first order conditions. We take the derivative with respect to C, so we see that marginal utility equals the shadow price. Then we have the co-state condition. How should we optimize, how should this value of oil, the shadow price of oil, increase over time? And this is the general formula. And now we see that actually in the Hamiltonian, S is just absent. And if that is the case, we get this simple formula that the shadow price should, the growth rate of the shadow price should be equal to the discount rate. And that is known as the Hotelling rule. Key concept. So if you have nothing in your Hamiltonian depends on S, your shadow price has to increase at the discount rate. Applies to any non-reviewable resource. Will also apply to the carbon price if we do cost minimization to stay below a given temperature. And so what is the logic of this result? That I can get the oil out of the ground, exploit the oil, sell it or enjoy it, and then no, maybe that is a bit. No, I'm going to tell that this only next week. So what is the logic of this? Is that the present value of consumption should be constant. So if oil is just, I have this cake, it's my oil well, and I'm going to live off the oil, and I live a very long time, maybe capital T, the end period is maybe very high. So each marginal utility, the value should increase because future consumption is less valuable than current consumption, but the present value should be constant. If at some point the present value of my marginal utility of oil is high and then the present value is low, there are arbitrage gains. I can consume less this high period and more in the low period, and I will increase my present value of the total value. Yeah? Let me maybe show this. So the Hotelling rule says that the shadow price should increase at the discount rate. But that actually means I don't value every period the same way. In present value of the shadow price, it imposes a constant shadow price in present value terms. Because imagine that I have high value tomorrow, and then lower value in the future. It's always better to consume less today and give more, consume more in the future. Whenever there's inequality, I have opportunities to reorganize my consumption pattern to improve. Yeah? So now that we have this Hotelling rule, we have a differential equation. And to find a solution, we're going to integrate the differential equation. So we'll do that in a seminar. I can tell you a differential equation that tells you the growth rate is constant gives you an exponential increase. And obviously at time 0, you were at this initial shadow price mu. But you don't know the initial shadow price. But what you do know, by knowing that the growth rate is constant, you're going to get an exponential path. We'll do this as a three-line derivation. We do it in the center. So now let's add an element. We have isoelastic utility. So the form of our utility function, this is just for convenience. We're going to use this a lot in macro modeling. The next model will have this. For oil, it's not that often, not a very good function. We will see next week a better one. But this is a very standard function in economics and has this nice property that for 0 consumption, you get minus infinity for marginal utility. So you never want to go there. And so marginal utility has this simple form, c to the power minus eta. Now, why is this a constant isoelastic utility? If I take the elasticity of marginal utility with respect to consumption, I get this minus eta. Yeah. It's called in finance literature constant relative risk aversion. Gives you the same formula. Now we can also see what happens. How does this marginal utility change over time? So remind you that if you have the chain rule, so you take the time derivative of a function of an argument that depends on time. You take the derivative times the argument, so over time. So you know that the marginal utility will be the second derivative times the change of consumption. So if we want to calculate mu dot over mu, because we want a differential equation in consumption to establish our optimal consumption path, we know that mu equals marginal utility, so it's the relative change of marginal utility over time. The time derivative of marginal utility, I just calculated it here, divided by UC, and you get this simple expression, minus eta times the growth rate of consumption. So in our case, having a growth path for the shadow price allows us to derive a growth path for consumption. Turns out by a convenient choice of functions that it's again a constant growth path of consumption. In this case, it's going to be a degrowth path. So we had the hoteling rule saying that the growth rate of the shell price equals a discount rate, and I apply this to my outcome, and so now I see that I have this solution. The growth rate of consumption is minus delta over eta. So now I know that consumption is going to follow an exponential decreasing path. Maybe I quickly show this how we do this. So we have this solution, the change C dot over C, but I write C dot explicitly. Then I bring delta T to the other side. So now I have separation of variables, consumption at one side, time at the other. I integrate both sides. And so the integral of 1 over C is log. The integral of a constant is t, and this is my solution. It has a constant, an integrating constant, which I can find by, first rewrite it differently. So consumption at any point in time is this exponential growth function. So here I have shown you that if you have a constant growth path, you'll get a exponential, if you have a constant growth rate, that's what we start from, you will get an exponential path for your solution. And to give some meaning to the integrating constant, if I just say I call my consumption at 0, C0, there must be some initial consumption. For now I don't know it, but let's just rewrite the constant as C0. So I put in what happens at time 0, I get consumption at 0, so I can write it this way. So this is my, now it's an exponential degrowth path. So that is something that starts from the level of any consumption at time 0 that we don't know yet, and then it has this shape. Okay? I know the degrowth rate, so it tells me that it is delta over eta. Delta makes sense because if I am very impatient, I want to do this after, eat more early and then eat less, consume less later on. Now, eta is actually the contrast between low consumption and high consumption. It's my inequality aversion. We'll come back to that. And so if I'm high inequality aversion, I'm on the black line because I hate to have this low consumption later on, and I want to spread better out, like spread out more evenly my consumption. Yeah. And that's it. Now, we haven't really found C0, and we'll do that in the seminar, I think. Yes. Let's see. Yes, we're going to do this in the seminar. So here are a few solutions. So depending on if the most intuitive is time have to have a very large time horizon, and you get this profile. For an infinite time horizon, we would get something like this. And how do we actually find this? That's the slide that I have skipped. We said the area under the curve, my consumption summed over all periods, that's going to be my initial sum. So if I take, if I'm on the black part, initially I consume 100 barrels, then I consume 90 barrels, 70 barrels. And if I take all these barrels that I have over the entire future, that must be equal to sum. And so what I'm going to do to find C0, I'm going to calculate this integral, and that will fix my C0. But we'll do that in a second. Similarly, what you can then see here is that the integral under this function is going to be the same as the area under this function. Imagine that I die in 5 years and I don't want to leave anything for my kids or whatever. This is my optimum. So I consume a lot of oil and then I die, etc. So you can choose your end period and it will come out of that end period. Yeah?
Are you consuming everything? Wouldn't you like even like further down to the bottom?
So here, for example, so by design, that was how we will find initial consumption. But the area under any solution, so here is the area for t 10 years, should be equal. It's going to be each time equal to the initial stock. Okay? That's how we find initial consumption. Because with my solution, the hoteling rule only told me shadow price should go up at the discount rate. We know from the shape of the utility function that means consumption should go down at some delta over eta. But then the question remains what is my starting point? Yeah? So this these are two lines that decrease at the same degrowth rate. Yeah? They are both compatible with the hoteling rule. But I need an initial condition, or in this case, a terminal condition saying consume everything that will fix the initial consumption. No worries, seminar, we're going to do this more. Questions? Yes.
If the model is supposed to find the optimal consumption, why do we put the constraint of we need to consume everything? Wouldn't it just know to do that?
So that comes out of the transversality condition. I'll come back to all the transversality conditions in 10 minutes. So here is another example. The Ramsey growth model is the basic model for macroeconomics. So we have capital, consumption, utility, discount rate, and a production function. Production only depends on capital. There is no labor in this model. We are going to maximize utility. So it's the same equation as for the oil model, the hoteling model. So here, the dynamics of capital are a bit more complicated. So if you take your production minus your consumption and minus the depreciation of your capital, so the depreciation rate is sigma, that allows you to increase your capital. Yeah? So production minus consumption, that is your investment, minus the gain is then your increase of production. In the long run, this is going to be zero. Like you're in a steady state and things are constant. Good. And you know how much capital you have at the start. Capital cannot be zero, but it will not be 9. Good. So Hamiltonian, same thing. Utility, and then the change of capital times mu. If I know how much capital I lose or build in a model and I value that at the correct price, then that is my contribution of that period to my total welfare. That is actually gross national product. So it's your consumption, what you produce, plus the increment in capital is also part of GDP. GNP. Yeah? That's how we do welfare calculations on sustainability for GDP. Good. So first order condition, same logic, marginal utility equals the shadow price of capital. We value capital at its marginal utility. Then the co-state equation, this is the general form. Now this is a bit more complicated because the Hamiltonian depends on K. We have here production depends on K and decay depends on K. So we have marginal production minus decay, and that is multiplied by the shadow price. So now we have, I can bring mu, divide the whole equation by mu, and I can write it in the more intuitive form. So on the one hand, I have opportunity cost of waiting. If I consume a bit later, bring one consumption unit from today to tomorrow, I lose my patient. I want at least my discount rate. I want more tomorrow than today. I need a return on that to be happy, to be indifferent. The return that I need is the pure time preference rate, my decay, my discount rate. What do I get in return? I get the return on that capital, net of decay. Yeah, so this is the net return on capital, but I also have to take into account that I will value that my shadow price changes over time. I probably value that capital less if I'm on an increasing consumption path, if this is our humanity. So this is going to be the increase of the shadow price. We have already calculated that. That is actually just minus eta times C dot over C, the growth rate of consumption. And now we got the very famous Ramsey rule. So the discount rate is the return on capital, the net return on capital, and should be equal to the pure time preference rate plus my inequality aversion times the growth rate of the economy. We'll spend 2 hours on this in week 4. This is the basis for discount. Now, it's also the most famous macro model, and so once you have the tools, this can be done on 2 steps. Yeah? So then, how do we find what happens in the long run? This model has like a steady state, and if we set all changes equal to 0, we get this in the steady state. You get the pure time preference rate plus the decay rate equals the return on capital. That is called the golden rule, the modified golden rule. An older version before this method was popular, you had the golden rule saying that the return on capital is the decay rate. But that actually sets the pure time preference rate to 0. It's not really precise. Questions for the Ramsey growth model? Then I'm gonna, the forestry model is in the, we're gonna see that in the seminar. And then we have the, so interpreting the co-state variable, you can just believe me that the shadow price that comes out of this method is your marginal contribution of the stock to your welfare. And if you like a proof, this is a very a simple sketch of a proof, plus integration by parts and stuff like that. And so in the end, we show that it's the marginal contribution of extra stock on your welfare, on your value. More importantly is the transversality conditions. So we're going to see 5 cases or 6 cases. So let's first take the simple case where actually everything is fixed. And one way to represent this is if I have time, and this is my stock variable, I'm going to call it K because that was the last model. Can be the stock of oil, can be the stock of fish, can be the stock of timber. Yeah. One option to make this a meaningful problem is to say you're going to die at 80. So we know that. And I want you to give this level of capital to your children. Now the model is well defined. You maximize your utility until you're 80 and you know where to end with your capital. So you have two, so this model, you already know there are going to be two differential equations. One is the co-state equation showing you that the growth of your share price. The other is the dynamic to start with. We had S dot is minus Q. So since we have two differential equations, we need two constants. One is T at the end is 80, the other is K at the end is whatever. Yeah. Now you can also say, okay, I know when I die, but I have no limits, I have no constraint on how much capital to leave. So capital can end at any of these points, including negative. Yeah. So then capital is not ideal because actually capital is normally constrained to 0. But imagine that this is your savings account and you have like unlimited negative. Yeah. So now you should make sure that you have consumed so much until full saturation. So extra debt, you're allowed, like you have a credit card without limits and you die at 80. You want to finish at minus infinity or somewhere low at a point where your margin utility is 0. Extra trip to whatever or extra hamburger is just not going to add value. Okay, so you need, the condition is this capital should be worthless. Yeah, because there is no constraint. Yeah. It's not a perfect example. A better example will be temperature, where we can go to positive warming. We can also go to 0 warming, negative warming, which then we will set. Now, warming is not ideal because normally you don't have fixed time. There is no end of the world, so then it's again tricky. But just to make the general case, I want to treat all possible solutions. Then we have the more common case. We have a fixed terminal time, but this is a stock, like a physical stock, physical capital or oil. Yeah? Two things then can happen. You exhaust the stock, that's good. Imagine you didn't exhaust the stock and it's valuable. No way, this is optimal. You should have consumed more. Yeah. So if it's available, you need to deplete it. That's obvious. If you don't deplete it, it needs to be worthless. Two possibilities. Okay. So one of both needs to happen. So a compact way to write this is the product of these two things: the value of the stock or the distance to the constraint should be 0. Yeah. So I say cannot be 0. I can put any. I could say you're not allowed to consume more than whatever residual oil stock is left. That is the same. Mathematically, it's going to be the same. Yeah. You put this K bar instead of 0. Then we can have the situation where I say, I don't care when you stop. You optimize freely, but whenever when you stop, you need to stop at. So this would be an admissible path. or even this, but when you stop, you need to be at A. That gives you one constraint already. Like one, remember, you have two differential equations, you need two integrating constants. One is going to be n capital X now. The other is, when should you stop? And here is the rule. Your Hamiltonian should be 0. Remind you, the Hamiltonian is the contribution of this period to your general welfare. Imagine you stopped and it's positive. But you stopped too early. There was still value by extending your life. But imagine you have a life and you can have like negative, you can be depressive or something like that. You prefer to stop. Yes, it's not a good example. Stopping. Yeah, let's not do an optimal suicide example. It would be this, you solve it this way. So, optimal stopping. Imagine that the Hamiltonian is still positive. You should extend your period. Yeah? Imagine you stop and you see that it was actually negative. Yeah, you should have stopped earlier. Because it was like you were adding periods with negative value to your welfare. So then that means you should stop earlier. So in other words, you go until the marginal value of adding a period to your welfare goes to 0. Yeah. Good stopping problem. Having your company and you want to know when you go back or when you stop the company. Yeah. So and you have a target value of your company in mind for your kids or so. So you have a fixed target, and once you reach the target, like you can stop. But that is only interesting when the marginal profits are 0. If you're making still profits, you shouldn't stop that company. And if it's negative, you should have stopped earlier. You could have like dissolved the company and end up with more money. Yeah. So that's Would
another example be like retirement?
Yes. It's a bit complicated in the sense that the life after retirement still matters. So somehow that must be in the objective first. But yes, so there are many optimal stopping problems that are meaningful. Good. So then free time, so when the other possibility, is this so now we're going to say there is a minimum level to this game. So then two things happen. You also then, again, let's say the capital, you're at the boundary or it's worthless. Yeah? And then since this is optimal stopping, you can choose your end period, Hamiltonian end period should be 0. Now, what if we have infinite time? So the same logic applies to infinite time, but whenever we accept the shadow price should go to 0, you should actually remind you that in reality, we are talking about present value shadow prices. The present value shadow price is the true contribution to the discounted value function. Yeah? And so if we say shadow price should go to 0, we mean the present value shadow price should go to 0. So that means that the price, the current price, the price that you would see in the future periods should not increase faster than the discount rate. You are not allowing explosive price falls or shadow prices for your stocks. So And that is what is expressed here. So I define the present value shadow price as the discounted current value discount price, and this price should go to 0. Yeah? Meaning your current value cannot increase faster than the discount rate. Faster than the discount rate, think of it as the Ponzi scheme. Your debt, you're borrowing to pay back your interest, but then your debt is going to at some point get explosive. Yeah? And in infinite time horizon, it's also always going to be the case that the Hamiltonian, but the present value Hamiltonian needs to be 0. So if that's not the case, you have an explosive Hamiltonian. Again, think of a Ponzi scheme. So if this becomes infinitely negative, then something is wrong. Yeah. Good. So maybe on top of that, you have a constraint on capital. Think of the oil example. Negative capital cannot happen. So then, again, come as before. We have it's valueless or the stock is 0. Often the stock will be 0. Yeah? And or in the case of the Ramsey model, actually this one, it's a comment that comes later. If you really apply it and start looking what it does, it's going to impose you to go to the steady state. And I will see that in a phase diagram. If you're not on the steady state, at some point things go crazy and you will get an explosive path for your price. But that's a technicality. It's better to say sometimes if you don't see an obvious information from this fact that lambda cannot grow faster than the discount rate, that the shadow price cannot go faster than the discount rate, and there is a steady state, you can just assume you go to the steady state. And imagine that you have a fixed capital at infinity. That is a condition in itself, so you only need one transversality condition, and this is that. As I told you already, if there is a steady state, you can assume that you go to the steady state. So, in general, stock is going to be exhausted at the end. Or if it's not exhausted, it's worthless. And if you can freely choose your end of time, your stopping time, the Hamiltonian should be 0. Let me then conclude in 1 minute. Is somebody waiting? No, no, okay. So, sadly, static problems are rare. Most true like real world optimizations are happening over time, and there are trade-offs over time, and so we need dynamic optimization. So this is extremely useful, and then sadly extremely hard. So if you maximize welfare, profits of companies, so companies apply this to their profit maximization because they don't care just by profit for one period, it's the whole future that they're looking at, happiness, votes, etc. And then that applies also to environment. So most environmental problems have this have trade-offs over time, and so that's going to be very useful for the coming 4 weeks. You can have many state variables. That's quite obvious in theory. So you get a Hamiltonian with different shadow prices and different difference equations. You can have constraints on the decision variable, relatively easy. Constraints on the stock variable are hard. We're not going to see that. Even not on decision variables. We're just going to see, we're going to put the constraint on the stock at the last period. And if then the whole path is meaningful, like we never go negative with our stock, we're happy. So, and we will choose the examples in the way that they are, they satisfy this. We have no uncertainty in this model, so obviously this model also exists with uncertainty, and then it's called dynamic programming. It's a bit different, and I have slides that show that, but it's not exactly. No worries. Any question? We're going to do exactly the same for 4 weeks, and at the end it's going to be very easy. Yeah.
There's like a couldn't there be visual illustrated like a stable state that's constantly above or below?